Hi, my name is Manish Gupta, and in this video, I'm going to talk about DALL-E, which is a zero-shot text-to-image generative model. So let's start with a quick overview of DALL-E. It's a model to interpret the natural language inputs and generate high-quality images. In some ways, you feed a caption as input, and it provides an image suitable to the caption. For example, if you feed in things like a tapir made of accordion, you see it nicely combines the properties of an animal with the properties of an accordion. Either the accordion forms the neck or it sort of forms the leg and so on, right? You can also feed in captions like a baby hedgehog in a Christmas sweater walking a dog. And you see, in many cases, it sort of works fine. Of course, it sort of screws up in some cases where a hedgehog is actually not walking a dog, but walking a hedgehog. However, there are interesting other capabilities like a neon sign that reads back prop. So it creates such creative, nice signs. Or you could also do interesting tasks like image to image translation. So the exact same cat on the bottom as a sketch on the bottom. So this is like a sketch generation task being done by DALL-E. It was revealed by OpenAI in a blog post in January 2021. Of course, there's a DALL-E 2 also out now. Um, the DALL-E is a 64-layer GPT-3 model that models text and image together. It's like a multimodal model. It does so autoregressively, just like GPT-3, and it has 1280 sized inputs, of which 256 are text tokens, and the remaining 1024 are image. The name DALL-E is essentially a combination of these two characters, the character Wally by Pixar, and DALL-E comes from the Spanish surrealist Salvador Dali. So it's a 12 billion decoder only transformer model, which is trained on 250 million image text pairs. So it's a quite aggressively trained in a very exhaustive manner. The training consists of two stages. So the stage one is essentially an unsupervised kind of a stage where you train a discrete VAE, discrete variational autoencoder, which tries to compress 256 cross 256 RGB input images into a 32 cross 32 grid of image tokens, where each element follows a vocabulary of 8,192 possible values, right? The second stage essentially is it sort of takes a 32 cross 32, that is 1024 image tokens from the first stage, or the dVAE, the discrete VAE encoder, and by using argmax sampling, and then given the text and the image pair, you byte pair encode the lowercase caption maximum 256 text tokens, and then you combine it with your 1024 image tokens so as to overall get the input for learning a multimodal autoregressive model, right? So for the text, the vocabulary size is fixed to 16,384, and the model that is trained is autoregressive GPT-3. It sort of jointly tries to model the distribution over text caption and the image text caption and the image tokens, right? Now, modeling this thing is a little difficult, and therefore, what DALL-E does is variational inference-based training. So the idea is, of course, ideally to maximize the joint likelihood of the images X, captions Y, and the token Z, which are a representative of the image given the dVAE, right? However, rather than modeling probability of images given the caption directly in an autoregressive manner, what DALL-E does is to essentially factor the distribution in terms of the discrete VAE's compressed 32 cross 32 grid representation of the original image, right? So thus the joint is sort of factorized into two different parts, X given YZ and Y comma Z. And then given this factorization, the variational inference essentially tries to maximize the evidence lower bound, as is popular in variational inference literature. The lower bound is essentially given by this, right? So as you notice, the lower bound actually has three components. These three mainly. So the first one essentially tries to minimize, or rather, the first one tries to optimize the probability of the images given the captions, right? This one is trying to of the images given the latent, right? Latent representation from the dVAE. The second one is trying to maximize the probability of these latent given the original images, and the third one is trying to sort of optimize for for the distribution of the captions given the latent captions and the latent, right? So that's that. So the as you can notice, the discrete VAE tries to optimize these two parts, the P theta and Q phi. Essentially, in fact, the encoder is trying to encode X to Z, which basically means it's trying to optimize for Q phi, while the decoder tries to optimize for P theta. That is the probability of generating the original images X back from the latents Z, right? Um, the transformer tries to optimize the P phi. So the third term is actually being optimized by the transformer. We'll see in details each of these stages in the next few slides. The interesting part is by doing this factorization, DALL-E doesn't really learn to predict every pixel in the generated image. Rather, it predicts a sequence of image latents, right? So essentially, it's trying to the transformer is being used to just generate a few latents. And then it leaves it to the discrete VAE, the decoder of the discrete VAE, to actually convert those discrete latents into really high quality images, right? So by allowing the transformer to actually just model the latents, the idea is that the transformer is relieved of the burden of actually caring for small of small high frequency details, and rather the transformer actually focuses on the big picture, while the dVAE sort of the discrete VAE handles the smaller details. Yeah. Here is a double click through into the first stage, which is learning the discrete VAE. So the steps are actually nicely shown in these illustrations. These illustrations come from this nice blog post. So in the first step, you take the image and you feed it to a CNN encoder. The CNN encoder essentially gives you so it takes this 256 cross 256 cross 3 image, right? Because RGB image, it gives you 32 cross 32 cross across the number of code book vectors sized representations, right? So essentially 8192 possible values. So essentially the output from the CNN encoder is 32 cross 32 cross 8192, right? So the encoder outputs distributions over these codebook vectors. So the idea is that DALL-E has this notion of storing one vector which represents 8192 vectors, which sort of represent some sort of a basis, right? And then the encoder, the CNN encoder, is responsible for outputting a probability distribution, a categorical probability distribution over these 8192 different codebook vectors. So discrete VAE essentially maps images to a discrete space in some ways. And then these codebook vectors, well, how are they trained? Well, they are also trained using stochastic gradient descent, just like the encoder and decoder networks of the discrete VAE. So this part is clearly the encoder part, and this part is the decoder part. Now, let's say we already talked about the encoder, and what the encoder is trying to do is to basically output a distribution over codebook vectors. So as we discussed, it's sort of for every pixel. So for each of those 32 cross 32 cross 8192, it's sort of giving for every position, it's giving a 8192 sized vector, right? And each of those values are basically logits for deciding the probability contributions from each of the codebook vectors, right? Now, let's call those encoder outputs as Q. So at a particular position, let Q EI given X be the softmax probability for the ith codebook vector, right? Out of K. So if the K codebook vectors, then let EI be the ith be the Q of EI given X be the probability for the ith codebook vector. So then, if we were just doing typical computations, we could we need to sample a latent, by the way, right? We need to sample a latent from based on this distribution, so that we can use it as a representative for this particular position among the 32 cross 32 grid, right? And then, of course, this latent can then be used by the decoder so as to decode the entire image back. Now, the typical way of doing this is as follows. You could sample latent by actually looking up the codebook representation for argmax of I, where where the argmax is taken over gi plus log of q of ei given x. So remember, the q of ei given x is basically the probability associated with the or the logit value associated with the ith codebook vector for this particular position from the encoder. However, you also want to bring in randomness, and therefore you use GI. GI is basically a random variable sampled from Gumbel distribution, right? So that's that. That brings in randomness rather than you picking up the most probability one in every case, right? However, the problem with this kind of a representation is that argmax is not differentiable. And since argmax is not differentiable, the typical trick that is done to handle such situations is to do something called as the Gumbel softmax relaxation. In simple words, it basically just means that rather than argmax, you end up using softmax, right? So you replace this kind of a computation by a softmax kind of a computation for the ith codebook vector, right? So the contribution from the ith codebook vector is going to be computed using that formula, using the softmax normalization formula in some ways, right? Once you have that, you sample from the softmax now and produce these yi's over the set of codebook vectors. So if you have once, if you have basically, let's say 819 to codebook vectors, well, you will create 819 to different yi's, and then you'll say that, hey, the z for this particular position is going to be a summation over all of those 8192 codebook vectors, right? So as you see, here are these codebook vectors, which are represented here. And for every position, the encoder is actually generating a distribution over those 4 codebook vectors, right? These are basically Q of EI given X, EI given X, where I is equal to 1 to 4 here, because in this picture, there are only 4 codebook vectors. Right? Now, uh, you take that, but then at the same time you apply yi, you compute yi's. So essentially, for every position, you're going to compute yi's, and then you multiply those yi's by ej's. So or you take those yj's and multiply by ej's so as to get the z. Remember, this is the z for that particular position, and if you have 32 cross 32 positions, yes, you will get 32 cross 32 z's. Now you take this latent, z's, and then you feed them to a decoder, which basically helps you decode the image back. Okay. So that's that. That's basically how the first stage works. Now, more details. The discrete VAE in this particular case uses convolution neural networks, particularly ResNets. And ResNets typically have 3x3 or 1x1 convolutions, right? The encoder clearly produces 32 cross 32 8192 outputs, as we discussed in the previous slide, which are used as logits for the categorical distributions for the image tokens, right? Encoder uses max pooling operation, decoder to do pooling, to do downsampling, but the decoder uses nearest neighbor upsampling, which is what they observed to work the best. There are more details, like for example, they varied beta and the relaxation temperature tau, which is used in the Gumbel softmax relaxation. They also varied the step size for the step size, while doing training. Okay. Now, why use dVAE? Well, the discrete VAE is useful because if you were not using discrete VAE, remember, if you were feeding 256 cross 256 kind of images as some sort of tokens to a transformer, you would require a very large input size for the transformer. So the discrete VAE very nicely helps you to reduce the input size, right? So that's the major contribution of this first stage of the training, which is discrete VAE, right? Now, discrete VAE basically does lead to reduction in the quality of the image slightly, but as you notice, the major part of the image does not change, right? So there are some things which sort of get lost while doing the discrete VAE. However, the main looks of the image, the main features of the image are still pretty recognizable. Second stage is basically the transformer stage in DALL-E. So the transformer essentially takes, as you can notice, text tokens as well as image tokens. Okay. So 256 positions are reserved for text tokens. So if the caption is less than 256 tokens, then essentially it is padded using a padding token, which is specially learned for every position. Okay. It's not the same padding token used across, but a padding token per position is learned. Uh, each of those representations are 3968 long. So that's the dimensionality that DALL-E uses, pretty large dimensionality at that, right? DALL-E has 64 attention layers, of which 62, each of which actually use 62 attention heads. So again, pretty massive in that senses, in that senses, right? So the text-to-text attention is the standard autoregressive kind of causal mask. However, the image-to-image self-attention actually follows 3 different kinds of masks: a row mask, row attention mask, basically paying attention to pixels in the previous row, or rather, the one row in that senses, right? Or it uses a column attention mask. These 2 masks are actually both column attention masks. It's just that this is more optimized version, right? Or it could use a convolution attention mask. So this one is shown for a 4x4 or a 3x3 kernel. However, in actual DALL-E, well, it uses a convolution attention mask for a 11x11 kernel. Okay. Now, not all of these are used in every layer. Well, last layer actually uses 11x11 kernel-based convolution mask. However, the other 63 layers essentially, depending on this formula, they either use the row attention mask or the column attention mask. The training loss function is the standard cross entropy loss function. However, cross entropy is computed both for text and image here. It's just that the image generation is more important. Therefore, it is given 7x more importance compared to the text generation. Okay. So it's a nice illustration for how the stage 2 works. You feed in the caption tokens, text tokens as input. Of course, you also do padding up to 256 different tokens, right? You feed the image latents that are generated by the first stage. Remember the encoder of the first stage, 32 cross 32 here, right? And then the idea is that in an autoregressive manner, the first step while training is to predict a distribution for the next image latent in the sequence. And then once you have this distribution, you sample a latent from this distribution, and this sample is actually input the sample back into the transformer and repeat, right? So essentially you take the sample input and then repeat. Of course, there could be teacher forcing as well at train time, but then at test time, of course, you sort of sample the latent from the distribution and feed the sample to the next position in the transformer. Okay. So at test time, well, once you have the transformer generated image latents, you would essentially take these latents and do a lookup in the dVAE code book and feed that to your decoder, and the dVAE, the discrete VAE decoder, is then going to give out an image, right? So that's basically the way you're going to essentially do the training, and then at test time essentially use it to generate the images. So putting it together, well, DALL-E comprises really of two stages. The first stage is done so as to, in an unsupervised way, sort of train the dVAE, the discrete VAE. And then in stage 2, essentially you feed the caption and hope to be able to generate the image, right? So in the stage 1, where discrete VAE, well, this was the encoder part, where the encoder essentially generates a distribution over codebook vectors, which are also trained while doing SGD, right? And the decoder essentially tries to decode these codebook vectors by sampling from the latent using Gumbel softmax relaxation and so on, so as to basically make sure that it can reconstruct back the image, right? In stage 2, you essentially take the caption and the generated image latents. You essentially train the transformer such that when you take these latents and pass to the decoder of dVAE, it can actually reconstruct the image nicely. Okay. So there are other details of training. Well, the training has been done pretty rigorously. So it uses 250 million text image pairs taken from conceptual captions, text image pairs from Wikipedia, and also a filtered subset of the YFCC 100 million dataset. Right. The training was actually done using 1024 16 GB V100s. So because the model is too large, and therefore parameters had to be sharded across machines. Training is done using mixed precision mixed precision, right? And the authors basically also indicate that getting the model to train in 16-bit precision past 1 billion parameters is actually significantly difficult because of the underflow that happens with 16-bit gradients, right? DALL-E just does not depend on these two stages to come up with final output. In fact, several different several candidates are generated by DALL-E, and these candidates are sort of re-ranked using a pre-trained contrastive clip model. Okay? So this pre-trained contrastive clip model essentially takes a caption and a candidate image from DALL-E and assigns a score based on how well the image matches the caption. Right? So the authors basically observe that as you increase the number of candidates that are passed to this clip models for re-ranking, you actually obtain better results. In fact, that is why they use n equal to 512, as high as 512, generate 512 different candidates, and essentially observe, essentially pick the best ones that are suggested by the clip model. They saw that up to 32, there is a very, very clear trend that re-ranking helps, but then after 32, it's sort of the gains are marginal. Yeah, but still they basically rely on 512 different images. Compared to other previous models, which were primarily GAN-based, we observe that DALL-E generates really realistic images, right? In fact, human evaluation on realism as well as accuracy shows that the DALL-E model essentially was chosen to be better than the previous best existing image generation model from text 90% of the time. So it's 90% of the time more realistic, and 93.3% of the time, um, um, you know, um, um, was highly accurate. So basically, better compared to DFGAN model in terms of the generated caption accuracy, right? So that's that. Now, there are several interesting characteristics about the kind of images that are generated by DALL-E. For example, DALL-E can clearly render familiar objects in familiar shapes, familiar polygonal shapes. But if you try to generate things like a hexagonal shaped manhole cover, it may not be able to find many interesting, or rather generate many interesting images. It's also observed that if you repeat the caption sometimes with a little bit alternative phrasings, then it improves the consistency of the generated results. So the more times you repeat, the better the kind of results that you observe. And there's a significant budget, 256 tokens, so you can repeat captions, important words in the caption, right? DALL-E can also map textures of various plants, animals, and other objects onto three-dimensional solids. For example, here a cube and made of porcupine, right? It can also try to generate images with repetitive objects. However, it is observed that repetitions above three are not very dependable. So sometimes it works, sometimes it does not work. And DALL-E can also generate multiple objects. So for example, you can try to generate a small red block sitting on a large green block. In fact, this is a very interesting problem popularly called as the variable binding task. The idea is that you are simultaneously controlling multiple objects, their attributes, and their spatial relationships all together in this task. And so, for example, if the task is a hedgehog wearing a red hat, yellow gloves, blue shirt, and green pants, the task is actually pretty complicated because DALL-E is not just required to come up with the hedgehog, but it is also supposed to follow all of those associations, like the hat should be red, or gloves should be yellow, and shirt should be blue, and pants should be green, and make sure that they appear at the right place on the hedgehog, right? So DALL-E sort of correctly responds to some types of relative positions, but not others. For example, it does very well in terms of putting up small blocks on top of large ones, but pretty bad in terms of putting large blocks on top of small ones. Also, when you talk about multiple colors, it can do good up to, let's say, three colors, but then beyond that, it sort of does not lead to very good results. Right? Yeah, so that's that. DALL-E can also help visualize perspective nicely. So, for example, you can come up with things like extreme close-up view or aerial view or rear view, and it sort of produces things in a very, very interesting manner. You could also basically modify the surface according to the chosen 3D style. So you could basically come up with 3D rendering in terms of something made of voxels versus something made of clay, and it renders them accordingly. In fact, it also renders shadows accordingly depending on the location, the sun, and so on. Right. Here is a nice three-dimensional rendering by DALL-E. So the idea here is that you of course pass a text caption, but you also pass an image prompt, and the idea is to be able to say that, hey, I'm giving you only a small part of the head in different orientations, and I'm then asking you to sort of recover the entire image. And these are top 25, top 30 different things that DALL-E generates. And as you notice, I mean, they're pretty nicely done. So in the sense that not just it sort of corresponds to Homer, but it also shows orientation depending on the orientation of the image prompt that was supplied. Right. DALL-E also does very nicely in terms of inferring contextual details. For example, you could basically ask it to generate something in a painting style or drawing style or chalk drawing, crayon drawing, charcoal drawing, and so on. You could also ask it to come up with something on a stained glass window style, or show something on cans, or write something on let's say neon signs, or write something on a bag of chips, and so on. And DALL-E very nicely tries to stretch the writing that was recommended, or according to the shape of the background, right? Context essentially. It also has a very nice knack of combining unrelated concepts. So, for example, in this case, nail and harp are combined in very, very creative ways in that senses. Again, here, avocado and an armchair are combined in in a very nice and creative manner. It also has some sort of some sort of knowledge about geographic and temporal notions. So, for example, you could ask it to come up with the flag of India, and it does understand, the geographic part of it. You could also, give it a text and an image prompt together, and then ask it to come up with a photo of Golden Gate Bridge. It clearly understands what Golden Gate Bridge is, but also, if you give it a prompt about evening time, it sort of generates evening photos. But if you give it a prompt of, let's say, night time or morning time, it will come up with those kinds of photos, right? It also has a notion of temporal understanding. So you could basically give it a prompt saying a photo of a phone from 1920s, and it'll basically come up with a photo of a nice phone from 1920s. So that's that. Then you can also do zero-shot image-to-image translation. So for example, you could ask it to copy the exact same cat on the top with a sketch at the bottom. So it comes up with things of that kind. Now, several times it's not exact. So for example, it's not really exact, but it does come up with very reasonable sketches in that senses. You could also ask it to come up with mirror images, or you could ask it to come up with, an original photo and a crop, an extreme close-up view crop of it at the bottom. So, so all of those are possible. Here are more zero-shot image-to-image translation tasks where you're asking it to come up with a red-colored photograph at the bottom, or one with IVR, or one with the stamp kind of a postage stamp kind of a rendering, right? Lastly, applications of DALL-E are pretty many, right? Here are some applications to fashion and interior design. So here is a male mannequin dressed in orange and black flannel shirt and black jeans. So that's pretty awesome. And similarly, you could come up with a female mannequin with a black leather jacket and gold pleated skirt. You could also use it not just in fashion, but also use it for interior design. So here's the living room with two armchairs, white armchairs, painting of Colosseum. So as you see, how would you place the painting of Colosseum? Now, there are so many awesome creative ways of doing it here. Right? For a typical interior designer to come up with these kinds of drawings, it would take a much larger amount of time rather than just choosing some reasonable ones from the top few which are shown by DALL-E. Okay. So to summarize, in this video, I talked about DALL-E, which is a 12 billion parameter multimodal 64 layer GPT-3 model. It is very popularly used these days for generating images given a text caption. It involves two-stage training, where the first stage is basically an unsupervised discrete VAE, while the second stage is a multimodal transformer. It's trained very, very rigorously, 250 million image text pairs, and using 1024 V100 machines, right? V100 GPUs, right? The transformer uses, of course, text-to-text attention, but also uses image-to-image self-attention masks with row, column, or convolutional attention masks, right? And lastly, it's not by itself. DALL-E is combined typically with the clip so as to re-rank the top few generated ones, and then it basically provides the one which is ranked right at the top by clip. So that's about DALL-E. Thank you for watching. Hope you liked the video. Visit my homepage and LinkedIn to connect or to know more about my research. Thank you.